Welcome to the video for chapter 27. Today we're going to be talking about what happens when the line is not just going to be receiving a steady state signal, but when that signal could be varying with time. And in particular, we're going to look at two cases. One where we close a switch and then a voltage rushes down the line and can reflect back and forth between the line and the load. And then we're going to talk about what happens when we send a narrow pulse along the line. And that narrow pulse can have some interesting behavior as well. It's also going to have a reflection and a transmission, and we're going to see that in some ways the narrow pulse has a lot of similarities to the regular transmission of a signal. So our goal for today is to talk a lot about bounce diagrams. And bounce diagrams, we've actually already seen them. We may not have used that terminology, but bounce diagrams were useful when we had that thin layer of dielectric. And today we're going to be talking about something that's a completely different physical circumstance when we're talking about a transmission line. Could be, miles long, but nonetheless, it's still going to have a similar behavior. We're just going to formalize it a bit more. Our historical perspective today is Granville Woods. He was an American engineer and inventor, and in particular, he was the first person who figured out how to be able to send telegrams to trains while they were moving. And that was a really remarkable accomplishment. It was sent over lines that were adjacent to the trains, and so that was a big deal. And then he obtained more than 50 patents. He was quite a tremendously prodigious inventor. So let's talk a little bit about what happens when we have transient effects. Up until now, when we talked about transmission lines, it was always a steady signal. Now, it may have been a sinusoidal signal, so it may not have been constant, but it was always going to be steady, where we were always sending the same signal. And we could see that signal had been turned on forever, and that it was never going to be changing. Of course, that's not realistic. Generators have to be turned on, batteries have to be switched in, signals can change, the transient behavior of the line will be very important to us. And so we really need to know what's going on at the beginning, because sometimes it'll work in steady state, but it wouldn't work right at the beginning. So first, let's consider what happens when the generator is a DC battery. And so we're going to model the DC battery by a combination of an independent voltage source and a resistor. That resistor, of course, Z sub B, would be the internal impedance of the resistance. So there is no 3 or 4 striped resistor that we could point to and say that's Z sub B. It is the fact that any physical source is going to have an internal impedance. You can't have a perfect independent source in the real world, and so Z sub B is going to represent that imperfection. You'll notice that we have a switch here that's closing at t equals 0, and when that switch closes, then we're going to all of a sudden see that voltage be applied, and it's of course going to race down the line. And there's going to be what we call a wave front. And the wave front is when we're going to have a transition between what was probably 0 volts in the past to whatever the initial pulse is going to be. We're going to call that initial pulse V sub 1. So V sub 1 is going to be the initial pulse as it's flowing down the line. Now, of course, unless it is the case that the line is impedance matched, in which case Z sub L is equal to Z sub C. If it's not impedance matched, then we're going to get a reflection, and that reflection is going to be V2, and that V2 is going to race back down the line again, and that V2 is eventually going to hit the battery, and when it does that, it's going to see the impedance of the battery, the Z sub B again, and that Z sub B, unless it is perfectly matched with Z sub C, is going to cause a V sub 3 to race back down the line again. And when V sub 3 hits the load, then we're going to have a V sub 4 that comes back again. And you can kind of get the picture that we're going to have a signal that's bouncing back and forth between the battery and the load for really however long it takes to die down. And that can depend on the propagation velocity, the length of the line, and how bad is the mismatch between the 3 impedances here. But let's talk about this a step at a time. What we're going to need to worry about first is what is the amplitude of this V sub 1 pulse. V sub 1 is the most interesting of the pulses because it doesn't know what is attached at the load. If you think about it, V sub 1 only knows what's happening at the left end of the line. Let's imagine that this line is 10 million miles long. There's no way that it could be able to know what's attached to the load at the other end. So it only knows what's happening at the left end. And that means that it becomes essentially a voltage divider where we have the voltage V sub B, it's just a lowercase b here, a V sub B, which is being split between what we'll call Z sub B and then the impedance of the line, which is Z sub C. So the very first pulse, V sub 1, is going to be done as a voltage divider. And so that voltage divider, we can write equation 27.1. You've been doing voltage dividers for some time now, and you can see that we're splitting V sub B across two resistors, and the resistor that we care about, the voltage, the V sub 1 up here, is going to be across the line. And so we take the resistance that we care about, and we divide it by the sum of the two resistances. So that's equation 27.1. And then how long does it take for that pulse to reach the load? It's going to be a time tau, and this should say tau, not t. So it takes a time tau to reach the load. Tau is the length of the line divided by the velocity of the line. And then don't forget that we also know that the velocity is the speed of light divided by the square root of epsilon r. We've used that a number of times. So when V sub 1 reaches the load, part of it's going to reflect back to the left, again, unless the load and the line are perfectly matched. And the reflection coefficient, which we've seen before, is going to look like this. Z sub L minus Z sub C over Z sub L plus Z sub C. Then that second wavefront, V2, when it hits the battery at a second tau later, so 2 tau later, it's going to hit the battery, and that's going to have a reflection coefficient, which is Z sub B minus Z sub C over Z sub B plus Z sub C. So we're going to see that there's going to be reflections, bing, 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 going back and forth along the line, and ultimately the voltage is going to be the sum of all of those wavefronts. It's going to be V1 plus V2 plus V3 plus V4 plus V5, all the way out. Now, typically what we're going to find is that these reflections are going to grow weaker and weaker and weaker. So we will approach a constant value, and it depends. Some lines would approach that value after maybe 3 reflections. Some would take 6. Others, if there's a lot of reflections, you might still be able to see the impact 10 or 12 reflections later. So what we're going to do is we're going to try to figure out what is the terminal value. The terminal value, the one that is going to be after all of the reflections occur. Now let's just take a minute and think about, in common sense, no matter how long the line is, as t approaches infinity, that line is negligible. If it's a mile long, then maybe as t is an hour later, certainly there's going to be no more reflections. If it's just a few inches long, then maybe you would find that after just a few microseconds there'd be no more reflections. But ultimately what we're going to find is that there's a different voltage divider, and that is V sub B with the internal impedance Z sub B. And then yes, there is a wire here, but it's going to be negligible. We're going to ignore that wire, and then ultimately the only thing that matters at the end is Z sub L. That's the load impedance. And then I'll call it V sub F. We'll eventually call it V sub F, V sub final. Is going to be the voltage that appears across that load as t approaches infinity. So while Z sub L doesn't matter at all at the beginning, it matters a great deal at the end. And while Z sub C is involved in all of the calculations in the middle, look how Z sub C appears in all of the reflection coefficients. It appears in V sub 1 and so forth. In the end, Z sub C goes away. In the end, it doesn't really matter at all. Let's prove that to ourselves mathematically. Now that we sort of have an intuition, we know that this is what the answer is going to be, let's prove it. So we know that V is equal to V1 plus V2 plus V3 and so forth. So we're going to take that sum. This is V1. We know that it's Z sub C over Z sub B plus Z sub C, and then there's a V sub B over here on the end. And so V1 is just that times 1. Now V2 is going to be that times the reflection at the load, because it's gone down and it's bounced back, and now it's going back toward the left. V3 has bounced back to the left and then back again at the battery, back toward the right. V4 has bounced 3 times, and then if we went on, V5 would bounce 4 times and so forth. Now, the thing to notice about this is that some of these terms have an odd number of gamma sub L factors, and half of the terms have an odd number of gamma sub L's, so that would include, say, for example, these two, and half of them have an even number of gamma sub L's. And we're going to split those two into 2 separate terms here. So everything that has we're going to split it into 2 separate terms here, one of which has an even number of gamma sub L's and one of which has an odd number of gamma sub L's. And then the one that has the odd number of gamma sub L's, we're going to factor a gamma sub L out of them. And so what we end up with here is 2 terms that are identical to each other, but they have, one of them has an extra gamma sub L in front of it. And each one of them is a perfect sequence where you're going to see that there is 1 plus thing plus things squared, and so forth. So we'll find that we're going to be able to simplify this using a mathematical expression. 1 plus x squared and so forth is equal to 1 over 1 minus x, as long as the magnitude of x or the amplitude of x is less than 1. So we can then apply that to the equation that we had, where x is gamma sub L, gamma sub B, and we end up with 1 over 1 minus gamma sub L, gamma sub B, and then we have a second term which has the extra gamma sub L, and then the 1 over 1 minus gamma sub L, gamma sub B. And we can now simplify that. We can get a common denominator, and then we can replace for the gamma sub L and gamma sub B, we can replace what we know in terms of the impedances. Z sub L minus Z sub C over Z sub L plus Z sub C, or Z sub B minus Z sub C over Z sub B plus Z sub C. We're now going to multiply through by this product right here. We're going to multiply the numerator and denominator by that common denominator. That gets rid of all of the denominators. Then we're going to cross multiply. We're going to FOIL each of these. So we have each of these 4 terms. We're going to need to do that product. A couple of places we're going to end up with negative terms. And so those 2 negative terms, it turns out, cancels with 2 positive terms in the other sum. So we end up with an expression that looks like this. If you'll notice, these 2 terms are identical, and these 2 terms are identical. And then these 2 terms are identical, and these 2 terms are identical. So we can simplify it like that, get rid of the 2's, and then we can factor out a Z sub L out of the numerator and a Z sub C out of the denominator. We can cancel this and cancel that. Then we can cancel this and cancel that. And what we're left with is a voltage divider for Z sub L and Z sub B, dividing the voltage across V sub B. So that's exactly what our intuition told us, but it's nice to have seen it proven mathematically as well. So we can do quite a few calculations with one of these systems. Let's go ahead and do the sort of initial calculations before we do a bounce diagram. Let's look at what happens when we have a 9-volt battery connected to a transmission that is a transmission line 20 meters long. Characteristic impedance of 50 ohms. The battery has an impedance of 25 ohms, and the load impedance is 40 ohms. So let me just write all of this out. We know that V sub B equals 9. We know that the length is 20 meters. V sub B is 9 volts. The characteristic impedance, Z sub C, is 50 ohms. The battery impedance, Z sub B, is 25 ohms. The load impedance, Z sub L, is 40 ohms. And epsilon R is equal to 10. So let's solve for V1 first. V1 is VB times Z sub C over Z sub C plus Z sub B. And that's equal to 9 volts multiplied by 50 over 50 plus 25, and that is 6 volts. So the first pulse that goes down the line is going to have a size of 6 volts. The reflection coefficient at the load is going to be Z sub L minus Z sub C over Z sub L plus Z sub C, which is 40 minus 50 over 40 plus 50, which is negative 0.111. It's negative 1/9. And that's not very much reflection, but 40 and 50 are pretty closely matched. So we're kind of fairly close to an impedance matched situation here. Let's check out what happens at the battery end. This is Z sub B minus Z sub C over Z sub B plus Z sub C. And that is 25 minus 50 over 25 plus 50. And that is minus 0.333. So not quite as well matched at the battery end, and therefore we're going to get more reflections at the battery end. The velocity is c divided by the square root of epsilon r, which is going to be 3 times 10 to the 8th over the square root of 10, which is 9.49 times 10 to the 7th meters per second. Tau, the time of propagation to go one length of the line, is L divided by V, which is going to be 20 meters divided by 9.49 times 10 to the 7th meters per second, which is 211 nanoseconds. and then V sub F is equal to V sub B times Z sub L over Z sub L plus Z sub B, which is 9 times 40 over 40 plus 25, which is 5.54 volts. So we can calculate these 6 quantities directly from the initial values that were given. There are some things that we can't do yet. We need a bounce diagram to be able to do them, but this is what I would consider to be the initial calculations that you need to do before getting into bounce diagrams. Now, a bounce diagram is simply going to show what happens as the signal bounces back and forth and back and forth and back and forth. And it starts at the bottom left-hand corner, and the first pulse goes that way. It hits the end, and then it bounces back and it goes this way, and then it goes that way, and then it goes this way, and that way, and this way. I'm going to show all bounce diagrams as having 6 bounces in this class, but in reality, of course, as a professional engineer, you have to use your judgment and figure out how many bounces are needed in each case. Notice that this is normalized so that each one of these, 1, 2, and so forth, is equal to 1 tau. So T divided by tau is 1. That means that T is equal to tau. T divided by tau is 2, means that T is equal to 2 tau. And Z divided by L, well, that means that this is the point that corresponds to L, and of course this is still the point that corresponds to 0. So it's going back and forth down the line. This is going to be the load, and this is going to be the battery. So what we can do is we can initially write the voltages of each of the wavefronts right up the line. I always start by writing the gammas. So gamma sub L would go here, and gamma sub B would go here, and V sub 1 would go right on this line. And of course then this would be V sub 2 and V sub 3. And we're actually going to calculate the values of each of these voltages. Then, when we want to find out what is the time-dependent voltage at any point along the line, we just figure out which of these wavefronts has already passed that point at the given time. It'll become a lot more clear after we do an example. So let's go ahead and do that example. We're going to complete a bounce diagram for the work that we just did. So for example 27.1, we're going to complete a bounce diagram. So I'm going to go ahead and write that gamma sub L equals minus 0.111, and gamma sub B equals minus 0.333. Those are the values that we had in the example 27.1. And we also know that this voltage, the first voltage right here, is 6.00 volts. Now when that hits the load end, it's going to be subject to this reflection coefficient. And when I multiply those two together, I get minus 0.666 volts. When it goes back to the other end, it's going to be subject to this reflection coefficient. And when I multiply those two together, I get positive 0.222. Then it hits the load end, and I get to minus 0.0247. And then it hits the battery end again, and I get 0.0082. And then it hits the load one last time, and I get 0.0009. So that died off pretty quickly because, again, the load and the line are pretty well balanced. Now, what we're asked to do is we're asked to find the voltage at the midpoint of the line. Now, you could be asked to find it anywhere, but the midpoint is particularly easy. And I like to draw a line right down the midpoint to remind me that I'm talking about the voltage at the midpoint. So let's take that midpoint. We're going to start at t equals 0, and that's right here. And at t equals 0, until I get to 1/2 tau, nothing has happened. So from t equals 0 to 1/2 tau, nothing has happened. But when I get to 1/2 tau, all of a sudden a wavefront passes me that's at 6 volts. So all of a sudden at 1/2 tau, I'm going to jump all the way up to 6 volts. And then I'm going to stay at 6 volts through tau. So once it gets to tau, then it has reached the load end, but then it has to bounce all the way back to the midpoint again. So that's at 1.5 tau. So notice that this right here is at 1.5 tau. So I come over here to 1.5 tau, and I say, what happens when I have 6 minus 0.666? Well, then I'm going to drop down to 5.333. So I like to label these so that I can keep them straight. There's 6.000, there's 5.333. And I'm going to stay at 5.333 until it goes down to, or back to the battery, and then back to the midpoint again, and that's at 2.5 tau. At 2.5 tau, I'm going to pick up another 0.222. And when that happens, I get to jump up to 5.555. I'll just say 5.55. Then I'm going to wait another full tau, which is going to be at 3.5 tau. And at 3.5 tau, I'm now going to pick up negative 0.0247. So then I'm gonna sort of take a small step down, and it's really hard to not overstate how big these last few steps are. It's like a dink dink like that. I'm gonna just step down to 5.53 volts. Then when I get to the next one, I'm gonna add 0.0082, and it just does that, and then it's gonna go up to 5.54. And then when I get the last reflection, that's only going to add this 0.0009. That doesn't even really change the 5.54. It sort of stays at 5.54 off to the end there. So the thing to remember is that when you're doing the bounce diagram, you have to figure out when does each wavefront pass that particular point that you're looking at. And in this class, we're really only going to go with midpoint and at the load. Now, if you were in professional practice, you might need to say, what happens when you are 90% of the way down the line? Then it would get a little bit trickier. You'd have to think about, okay, well, I'm 90%, so I'm going to be over here. That means that this won't happen until I'm, at 0.9 tau and so forth. But for now, we're just going to say we're either going to be at the midpoint or we're going to be at the load, and we'll talk about the load in a little bit. So this example shows what happens at the midpoint. But I do want to show you something really interesting. Remember this 5.54 that we just found graphically? If I scroll back up here, what did we calculate for V sub f? Wait for it, it's loading. V sub f was 5.54. So this value right here allows us to check our work. As a matter of fact, when I was doing this example the first time, I got it wrong. And I knew that I got it wrong because it didn't match the 5.54. So that's one really nice thing about these problems, is that you have the ability to check your work and know that you got it correct because you know what the final value has to be. So that's what happens if you want to do a bounce diagram at the midpoint. Let's consider what happens if you have a bounce diagram at the load. So what I really most of the time care about is what's the voltage look like at the load. And this is actually easier because it's going to have half as many transitions. If you think about it, let's scroll back up again. If I'm at the load, so if I'm way over here at the load, then I'm only going to have half as many transitions, right? Here there's a transition at the midpoint. Here there's a transition at the midpoint. There's 3, there's 4, there's 5, there's 6. But at the load there's only 1 and 2 and 3. So there's only half as many transitions, only half as much work to do. But there is a tricky part, and that tricky part I put in bold. The load voltage will not include the reflected voltage that just left the load end. So we have 6 volts coming in, right? And the load will definitely acknowledge that 6 volts. But the load voltage will not see the voltage that it just launched. It will not see its own voltage, in other words. Now, it will eventually pick up this minus 0.666, but not until it's gone all the way down to the battery end and then come all the way back to the load again. That means that when we get to here, we're going to pick up this voltage and this voltage. So we have only half as many transitions, but each of those transitions is going to pick up two voltages. In the same way, when I'm here at this location, I will not detect this voltage right here. It just launched, and I didn't see it when it launched. But when I get to this point here, I will get both that voltage as well as this voltage. Let's do an example. I think that that'll make it easier to see what I'm talking about. So exercise 27.3, perform the necessary calculations, draw a bounce diagram, and sketch the voltage at the load. So when I get a problem like this, the very first thing I do is circle or underline whether it says at the load or at the midpoint. For a setup in which the battery voltage is 100 volts, so V sub B equals 100 volts, and the battery internal impedance is 100 ohms, that's probably unreasonably large. You probably wouldn't have a 100 volt battery that had a 100 ohm internal impedance, but it makes the math easier, so I left it that way. The line impedance, Z sub C, is 50 ohms. 50 ohms. The load impedance is 30 ohms. And the line has a relative dielectric constant of 5. and the length of the line is 200 meters. So we can do our initial calculations. And the initial calculations are going to be figuring out what is the hold on just a second. What is the initial voltage? V sub 1 equals V sub B times Z sub C over Z sub C plus Z sub B. And this works out to be 33.3 volts. Gamma sub L is equal to Z sub L minus Z sub C over Z sub L plus Z sub C. And this works out to be minus 0.25. Gamma sub B is Z sub B minus Z sub C over Z sub B plus Z sub C, which is plus 0.333. The velocity is c divided by the square root of epsilon r, which it turns out is 1.34 times 10 to the 8th meters per second. Tau is the length divided by the velocity, which is 1.49 microseconds. And V sub F, the final voltage, is V sub B times Z sub L over Z sub L plus Z sub B, which turns out to be 23.1 volts. Okay, now we know that the reflection coefficient here is minus 0.25. Over here it's plus 0.333, and we know that the initial voltage that's going down is 33.3. Then the first reflection is going to be negative 8.325. The second reflection is going to be minus 2.77. And by the way, I'd recommend that you do calculate all the reflections first, because these numbers are going to be in your calculator. You know, I just calculated negative 2.77, multiply it by negative 0.25, and I get the next number. So that's going to be plus 0.693. Now that number's in your calculator, multiply it by this number, and so forth. So it really saves you a lot of trouble, and it also makes it so that you keep all the significant figures that are in your calculator. So I would recommend that you calculate all the wavefronts first before you do any other steps. Okay, now let's look at the time-dependent wave. We know that between 0 and tau, nothing happens at the load because the wave is on its way to the load. Now, when it gets to the load, again, here's the tricky part. It receives this voltage, but it does not recognize the negative 8.325. So it's going to jump up to 33.3. So that's right about here. So here is 0 volts, and then we know that we're going to be at 33.3. Now, how long is it going to take before 33.3 changes? It's going to take until 3 tau. So the next time that anything happens at the load, it's gone all the way back to the battery and then all the way back to the load. So nothing is going to happen until 3 tau right there. At 3 tau, now I'm going to pick up both this one and this one. So that's going to mean that we're going to drop down to 22.2. So 22.2 is going to be right about here. So there's 22.2 volts. And then it's going to take until 5 tau before the next thing happens. And then at the next one, we're going to pick up this one, and we're going to pick up this one. And when that happens, we jump up to 23.1. Whoops, somehow that line went away. And we jump up to 23.1, and that's where our problem ends. Does that match our final voltage? It does. 23.1 volts matches our final voltage. So we're feeling pretty good about this. We've figured out how to make these problems work out properly, and the bounce diagram allows us to figure out what's going on at the load or at the midpoint of the line. Now let's talk about what happens when we're going to send a narrow pulse down the line. And by a narrow pulse, I simply mean one in which delta t, the length in time that the pulse exists, is much, much less than the propagation time that it would take to go down the whole line. So if you think about the length of the line because the delta t is much, much less than L over V, then the pulse width is going to be much, much less than L. So we're talking about something that is flying down the line, but it has been turned off, or it has been turned on and then turned off again as it's on its way down to the load impedance. And of course, we have the characteristic impedance of the line. And the question is, what's going to happen when this narrow pulse hits that load impedance? Well, we know that it's going to start off, and let me just, I forgot to draw one thing in here. We have the generator back here, and the generator also has a generator impedance that we've, just like the battery that we just spoke about. And so I don't call this a battery anymore, but it's a generator because it's generating a pulse. And so a battery would just be turned on and stay on. Generator can turn on a pulse and then turn it back off again. So we're going to find that the very first pulse that goes down is going to be, again, a voltage divider, dividing the voltage of the generator across the voltage of the line and the voltage of the generator itself. Now, we know that when it hits the load, some of it's going to be absorbed by the load, and unless they are perfectly impedance matched, some of it's going to reflect back. And so the question is, how much is going to reflect back? And to try to make this be as general as possible, we're going to start with one of the most fundamental rules, and that is conservation of energy. We know that conservation of energy must be followed. There's no way that we're going to be creating energy here. We're not doing any sort of a nuclear reaction. So we know that the energy must be conserved. So if you think about it, we have the power of the incoming pulse multiplied by the time, the sort of time width of the pulse, is equal to the reflected power of the pulse multiplied by delta t plus the absorbed power of the pulse times delta t. The delta t's, of course, are all going to cancel out. So although it's conservation of energy, it's also conservation of power. So you could say to yourself then, oh, I see that the incoming or the incident power, part of it is reflected and part of it is absorbed. And the part that's reflected plus the part that's absorbed, that must be all of the power from the incident wave. Now, another way to write the power is v squared divided by z. You know, you've been using v squared over r. It's really the same thing as just v squared over z, but we have to be careful because there are two different z's involved here. So we know that the pulse that's coming in, that's the incident pulse, is going to have a voltage of v1, so we're going to have that v1 squared, and it's on the transmission line, so that's going to be divided by z sub c. Now, the reflected pulse, that's going to have an amplitude of gamma times v1, divided by z sub c, gamma times v1, the quantity squared, divided by z sub c. And then the part that's absorbed, well, that's going to be the load voltage squared divided by the load impedance. So notice that two of those terms have z sub c in the denominator, and only one of them has z sub l in the denominator. We're going to plug in what we know for gamma, and that's z sub l minus z sub c over z sub l plus z sub c. And now we start down a path of algebra. We're going to solve this equation for v sub l. And so as you can imagine, it means taking this term over to the other side, making it negative, multiplying by z sub l, that brings that over to the other side, and then this squared means we're going to have a square root. So you can see that that's where equation 27.22 comes from. We can factor out some common terms, and we can try to minimize this a little bit, and we end up with z sub l over z sub c times v sub 1 squared. That was common amongst both of these terms. In fact, it was the entire first term, so that's why this just becomes 1. And when we factor the z sub l, the z sub c, and the v sub 1 squared out of the second term, all that's left is z sub l minus z sub c over z sub l plus z sub c. We're going to do a little bit more algebra here. We're going to establish a common denominator because we need to simplify this. So I'm going to multiply the 1. The 1 is going to be multiplied by z sub l plus z sub c, the quantity squared. Don't forget that this term right here is squared. And so I end up with 27.24. I'm going to cross multiply those terms out, expanding the numerator, but then several of those terms are negative. And so several of the terms are going to cancel each other out. And we're left with equation 27.25. And then we can bring things out. We can bring things out from underneath the square root sign. The z sub c's are going to cancel. The v sub 1 is squared, so when it comes out, it just becomes this v sub 1. There are two z sub l's, so they become squared. When you pull them out, they become the z sub l here. When you pull the 4 out, it becomes the square root of 4, which is 2. And then this term is already squared, so it is no longer squared when it comes out of the square root. So we have an expression for V sub L in terms of V sub 1, and the transmission coefficient is just going to be V sub L over V sub 1, which is 2Z sub L divided by Z sub L plus Z sub C. Now, we derived a similar equation for the transmission coefficient previously when we were talking about discontinuities and dielectric constants. Now we're talking about transmission lines, so it's a different situation. And we also derived this one in a different way. So it's nice to know that we got this same result in a different way, but we got the same exact result. We can also go back to what we saw before, which is that T is equal to 1 plus gamma. And when we plug that in, when we plug in for T, we get our same equation for gamma that we've had for quite some time. So everything seems to be self-consistent. We know that if we have an incoming wave, an incoming narrow pulse that's going to hit a load, we can now calculate what portion of that wave is going to be transmitted. That's the T coefficient up here, equation 27.27. And then what part of it's going to be reflected, that's the gamma term here, that's 27.31. So let's apply this. We have a narrow pulse propagating along a line with a characteristic impedance of 50 ohms. So Z sub C is equal to 50 ohms. It comes to a connection with a line of characteristic impedance 100 ohms. So Z sub L is equal to 100 ohms. Because if you think about it, we have this first line, which has 50 ohms, and whether it is then terminated in a load, which could just simply be a resistor that's 100 ohms, or let me erase that part of it. Instead, what happens if it gets connected to a different transmission line? And if that different transmission line has a characteristic impedance of 100 ohms, well, then it looks to the 50 ohm line as though it has been connected to a 100 ohm load. So although this is a characteristic impedance of a transmission line, to the 50 ohm line, it looks like the load. That's why I've written Z sub L equals 100. The initial pulse has an amplitude of 12 volts, so V sub 1 equals 12 volts. What will be the amplitude of the reflected and transmitted pulse? Okay, so we know that we can calculate T. T is equal to 2 Z sub L divided by Z sub L plus Z sub C, which in this case is 2 times 100 divided by 100 plus 50, and that gives 1.33. We can also calculate gamma. Gamma is going to be Z sub L minus Z sub C divided by Z sub L plus Z sub C, and that gives me 100 minus 50 over 100 plus 50, which is 0.333. Now you might be troubled by the fact that the transmission coefficient is greater than 1. Transmission coefficient can be greater than 1, and it's not problematic if it is. We're gonna see that this still obeys conservation of energy, even though it seems like that would be violating the conservation of energy. Now we can calculate the amplitude of the transmitted pulse, and I'm just going to call this V sub T for transmitted. V sub T is going to be equal to V sub 1 times T, which is going to be 12 volts times 1.333, which is 16 volts. So that's the amplitude of the transmitted wave, and the amplitude of the reflected wave, V sub R, is going to be V sub 1 times gamma, which is 12 times 0.333, which is 4 volts. So we have a 12 volt wave coming in, a 12 volt pulse coming in, 4 of it's reflected, and 16 of it is forwarded on, which leads me into the next question, which is verify that energy is conserved in that situation. So we know that it's going to be power is being conserved because they all have the same pulse width delta T. So we know that P sub 1 is the incoming power. This is going to be V sub 1 squared divided by Z sub C. That is 12 volts, the quantity squared, divided by 50 ohms, and that's equal to 2.88 watts. And then we can say, what is P sub 2? That is after it has hit the load. That's going to be the reflected power, V sub T squared, divided by, and I should just call this Z sub C1, because now I need to call this Z sub C2, plus V sub R squared, divided by Z sub C1. Because remember, if we do think of these as being, here is Z sub C1, and then here, let's imagine this is Z sub C2, well, the incoming wave, that's going to be in the Z sub C1 region. The transmitted wave is going to be in the Z sub C2 region, and the reflected wave is also in the Z sub C1 region. So that's why these two get Z sub C1, but this one gets Z sub C2. So this would be 16 volts squared divided by 100 ohms plus 4 volts squared divided by 50 ohms. And that becomes 2.88 watts. So first of all, we verified that energy is conserved. Power is equivalent between the incident wave and then the sum of the reflected wave and the transmitted wave. But we also see that it's not fair to compare apples to oranges. It's not fair to compare amplitudes of the voltages in Z sub C1 and in Z sub C2, because this denominator down here is going to impact how much power is in that wave. Notice that when you get into Z sub C2, the same voltage yields less power because it has a larger denominator. So the fact that 12 volts comes in and 16 volts goes out shouldn't be troubling, because the energy, the power, is conserved, and it's really a difference in the characteristic impedances. So the big thing to take away from that, in addition to the equations, of course, is that if you have any sort of a discontinuity in the line, there's going to be reflections that are going to come from that. So let's imagine a couple of cases. You could have a transmission line, and maybe somewhere in the middle there's some sort of like problem with the line. Maybe the line got smashed, or it got crushed in some way, or maybe it got cut. And if there's any sort of a discontinuity, as the wave is coming in, it's going to detect that discontinuity. Part of the signal is going to go on, and part of the signal is going to be reflected. And the amount that gets reflected depends on how bad the discontinuity is. I mean, if it's pretty bad, then most or all of the wave can be reflected. But if it's not so bad, then only a little bit of it's going to be reflected. You could also imagine a circumstance, again, where you're going to have a change in the characteristic impedance of the line. And I try to exaggerate that by making the line look bigger. As the signal is coming in, some of it will be transmitted and some of it will be reflected. Or another case is you can have a line that's coming in and it could be split off. And as it's being split off, the effective characteristic impedance of the two lines is going to cause part of the signal to be transmitted on. In fact, it'll be transmitted on and split, but part of it's also going to be reflected back. And this, any one of those three circumstances is something that a company would want to know. Let's imagine that you ran a power company. Well, you'd want to know if there was a break in your line, or if there was a problem in your line. Or let's imagine that you run a cable television company. You would want to know that somebody was taking an extra copy of the line. You'd want to know about this case right here, because you'd want to know that somebody was stealing your cable. So we need to be able to detect anytime that there's a discontinuity in the line, and we can use time domain reflectometry to do that. Time domain reflectometry is just a really fancy way of saying we're going to send a narrow pulse down the line, and we're going to see if anything comes back. And if anything does come back, then we know that there's a discontinuity somewhere. And in particular, we can actually determine where that discontinuity is, because the time that elapsed between the initial pulse and the reflection represents the time of flight from the generator to the discontinuity and then back again. So let's remember that if you're transmitting a signal here and there's a discontinuity here, remember that you have to go L out, or we'll call that D out, and then you have to also go D back, right? It has to ping, and then it has to reflect. So D divided by V, this would be the time to go just one direction. We could call this sort of tau. But 2 tau is how long it would take to go out and come back again. So we know, actually, in this equation, we know delta t because we can measure. We sent out a signal, and 42 microseconds later we got a reflection. And we know v because we know all there is to know about our transmission line. So the only thing we don't know is d. And so I probably should have put a box around this equation, because this is the equation for time domain reflectometry. This simply says that if you know the velocity and the time, you can use this equation to find how far it is to the discontinuity. Now let's imagine that it's a dark and stormy night, and some of your customers are reporting that they're getting a power outage. You send a ping, you send a pulse out on the line, and it comes back a certain amount of time later with a reflection. You can now tell, you got your power lines here, and based on the amount of time that it takes for that pulse to come back, you can say, oh, it is somewhere between these two power poles right here. So I want you to go out and I want you to inspect those two power poles, and I want you to inspect, most importantly, the cable between those two power poles and find out where the break is and repair it. That's so much better than just saying, hey, somewhere along this highway over this 10-mile stretch of road, there's a problem. Instead, you can say between these two particular poles, there's a problem. That makes you as the engineer look really smart, and that really helps your company to be more efficient. Or you could say, there's a problem with this coaxial cable. Somewhere within this 10-meter range, something has happened to the coaxial cable. I don't know if it is that it's got an unauthorized split, or maybe the casing has broken and the water has gotten into it. But somewhere in this place, in this range, I need you to go in and find out what's going on. So being able to identify the location of that split is really, really helpful. So let's see here. We've got time domain reflectometry used to search for an unauthorized connection to a cable TV line. The transmission line has a relative dielectric constant of 12, and the reflection coefficient, or the reflection, is detected after 74 microseconds. How far away is the unauthorized connection? First of all, we calculate the velocity, c divided by the square root of epsilon r. This is 8.66 times 10 to the 7th meters per second. And then we can quite simply calculate d. This is one of those things that isn't nearly as hard as it seems like it might be. So maybe don't tell anybody how easy this is. Just make it look like it's a lot of work. But when we multiply these two numbers together, 74 times 10 to the negative 6th, and then we divide that by 2, we end up with 3,204 meters. And that is to say about 2 miles. Now, you might say, how many significant figures can I carry in that number? And the answer is it depends on how many significant figures are in this number, in the 74 microseconds. So here it was only 2 significant figures, so I technically should say 3,200. But it would depend. I mean, if you have a good oscilloscope, then you can probably detect that to 3 or 4 significant figures, in which case you can probably detect the location of that discontinuity to 3 or 4 significant figures. So that's it for today. We've seen how to handle when a switch is closed and power is suddenly applied to a transmission line in a load. We know that the initial pulse that goes out is v sub 1. We can calculate tau, which is the time that the propagation delay for one cycle. Not one cycle, but one trip down the line. We can calculate the 2 reflection coefficients, and then we can calculate the final voltage. And all of those things can be combined together into a bounce diagram to determine the time-dependent voltage on the line as a function of time. Remember, the voltage at any point is the sum of all the wavefronts that have passed, and the only exception to that is that the point is at the load. So if we're looking right at the load end, then it doesn't see the reflected wavefront. It generated the reflected wavefront, so it doesn't see it until it goes to the battery and then back to the load again. If a narrow pulse is launched toward the load, then the initial pulse amplitude looks like that. And we also have equations that are the same we saw for previous examples, but we derived them for this particular case, and we found that a happy coincidence, they're the same equations. And so we can calculate the transmitted portion of the wave and the reflected portion of the wave. And then for time domain reflectometry, we have an equation that allows us to determine how far away is a discontinuity given the velocity of propagation and the time between the pulse was sent and when the reflection was detected.